Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Catherine McKinley. I've been here. I'm going to have my 1-year anniversary this month, so but this is my first candidate to host, and I'm really thrilled to have Jason Mars here. He's been working on data center energy efficiency. Some of his work that we're going to hear about today has been selected for IEEE top picks, and they've influenced the way that Google is building their data centers, and I'm hoping to have him come here and influence how we build our data centers.
Thank you. I appreciate it. Hi. So today I'm going to be talking about a piece of work that's captured my interest for the past few years. And it deals with the architecture of warehouse-scale computers and how we build a highly efficient design. I've been looking forward to this talk, and I'm happy to be here. So let's begin. So the landscape of computing has been changing. Traditionally, when users thought of computing, they think of a desktop they go to do some kind of activity, work or play, and then move on with their daily lives. However, now we're always connected with highly mobile, portable devices, and much of our computation cycles live in these massive scale, warehouse scale computers. And as noted by Forrester Research, the cloud was a $40 billion market in 2011, and this will grow to a $241 billion market by 2020. So this is really the space that my work has been in recently, and a very interesting space for computer science in general. So here I show two pictures of two of Google's large-scale warehouse-scale computers. Each of these buildings are a football field in size, and each building houses thousands of servers and machines. On these machines, we run large-scale internet applications like search and mail, social networking, and so forth, maps, and so forth. These warehouse-scale computers are expensive, costing hundreds of millions of dollars to construct and operate, and this is growing. And my claim is they're inefficient, as the system and software architecture of these warehouse-scale computers remains in its infancy. Now, when thinking about improving efficiency in warehouse-scale computers, there's a number of optimization objectives and metrics you can consider. My work has focused on performance of software running in these warehouse-scale computers and utilization. And as noted by Louise Barroso and Urs Halsel, software performance and server utilization is critical for efficiency in warehouse-scale computers. So we're all familiar with performance. It's how well our software is running on these machines. However, utilization is a particularly interesting metric in warehouse-scale computers. This graph to the right shows the utilization of Google warehouse-scale computers over a fraction of time of one of their 2007 machines. So on the y-axis, we have the fraction of time, and on the x-axis, we have the amount of utilization for that fraction of time. And as you can notice, the hump of the curve indicates that we're usually around 30 to 40% utilization on average. And what we'd like to do is move this hump to the right to have higher utilization for a larger fraction of time. And to put these two metrics in perspective, a 1% improvement in either performance or utilization results in millions of dollars saved at the scale of Microsoft's and Yahoo's and warehouse scale computer.
So is that in that you don't have to buy the servers, or is that in that you turn them off so you're not paying for the energy? Where's that?
This millions of dollars? So it's you won't have to use the server. So basically, there is a cost model used. So when a product group wants to use X amount of machines, Google. Well, I've done a lot of my work at Google, but Google will actually put a price tag on how much it costs to use that many machines. And so if you can have a 1% improvement using Google's cost model across the entire infrastructure, you save millions of dollars worth of computing resources. So that's kind of where that millions of dollars really comes from. It's an internal model. But you can consider building a smaller data center for some fixed amount of work. Question?
So I'm curious about this curve. So it seems like if you have a data center and you're running at that utilization,
yeah,
if you had fewer machines, they'd be running at higher utilization. So can't you just trade off the number of machines you have turned on to change your utilization curve?
Yeah, so that's a good point. This curve doesn't include load, right? So this is the utilization when all of the machines are active in some way, right? So basically, there's a number of contributing factors to low utilization, and one of those factors has to do with the lack of co-locating things together on the same machine. So does that, right, so I know what you're talking about. Like, so basically you can have over like a month, you can have times when basically you're not getting as many queries on the data center. But I believe this curve, I could be wrong, but I believe this curve factors that aspect out. I could be wrong though.
Google's not going to show us if they're turning off or on their machines anyway, right?
Yeah, pretty much.
And I think you can assume that the server doesn't just do computations.
Yeah.
And a lot of wasted time is on things like accessing storage and other external resources.
Right.
And the more disparate you have, the more time you're going to have sitting around waiting for the network, the hard drive, whatever else going on.
Absolutely.
That you can't use a CPU for.
Right. So, and all of those factors that you just mentioned actually factor into having this utilization challenge.
So is this CPU utilization or just any part of the system?
It's compute utilization.
Okay.
Yeah. So we'll see shortly how we can start addressing that utilization problem. However, before we look into improving efficiency in warehouse scale computers, it's important to reflect on the design of these systems. So traditionally, companies have used a functionality first, efficiency second approach, where initially they use commodity components like off-the-shelf processors and open source software. They stitch these components together for functionality, and then they tweak these components for better efficiency as time goes on. The problem is commodity components were not initially conceived and designed for the space of warehouse scale computers. And when you start with these components, you may lose sight of unique characteristics in warehouse scale computers that are critical for a highly efficient design. And so system architects may have missed a key characteristic that steers that design. So I argue that we must rethink the system architecture for any characteristics we would want to design our systems to exploit to have a highly efficient system. And so the inside of my work, and one of the underlying threads of the work I'm presenting today, is one such characteristic has been missed, and that is the diversity in execution environments. So let me first define what I mean by an execution environment. So here I show, so given a task, its execution environment is the underlying machine configuration for which that task is running on, coupled with the co-running tasks on that machine at that given time. So the execution environment of this task is the Generation 2 Xeon with the co-runner that's running. And so inside of a warehouse scale computer at any given time, we actually have a number of various execution environments. We have different machines because as machines are retired or fail, new machines are brought in that are of newer generations. And we also have at any particular time in a warehouse scale computer, each machine is loaded with a different number of tasks already running. So as we say, take this identical web search job and we run it on 3 different execution environments, currently in warehouse scale computers, the entire system does not place tasks where they would like to run or where they run best. Tasks can't adapt at the machine level to events within the execution environment of the machine. And certain kinds of events we can't address or measure or manage explicitly, such as the interference between tasks. And this is critical for utilization. So these are all hard problems and precisely what my work looks at. But before we talk about those problems, you might ask, well, is it important to acknowledge this diversity in execution environment? And my claim is that this diversity in execution environment is key for a highly efficient design. And a simple experiment can lead us to this conclusion. So if we take 3 different machine configurations, when just looking at machine configurations, if we take 3 different machine configurations, these are actually production configurations you would find in a Google cluster. When we run these 9 large-scale Google web services across these different machine configuration, we observe a significant impact on the performance of these various jobs. Some applications like Bigtable here can observe a 3x difference in performance depending on the machine configuration. Other jobs like Protobuf, it matters little which machine it runs on. And we have jobs like search scoring and search and maps detect face where it'll prefer one architecture while other machines tend to prefer another. So we observe that task performance is heavily impacted by diverse machine configurations.
Do you have a reason why that, any intuition just from a high level why you see those big performance swings? I mean, is it clock speed or is it something else that's going on?
Right, so I do have that intuition. And by and large, it has to do with the diversity in the memory subsystem of the various architectures. So across the 3 architectures I've shown, we observe a very big variation in the cache sizes used, in the prefetchers that are used on those various architectures, and in the topology of the memory subsystem across these architectures. So we have a Generation 1 Xeon, which is a Clovertown Core 2 type architecture. We have an Opteron, Istanbul Opteron, and we have a Westmere, a Generation 2, in the Halem type Core i7, but earlier Core i7 architecture. So if you notice across these architectures, if you look at it, the cache sizes are very different, and the hierarchy is different, and the types of prefetchers and the effectiveness of the prefetcher is different. That's our observation as the biggest contributor to the variation.
Maybe I'm caricaturing your argument. Would it simplify to say that the CPU runs at infinite speed and all delays are always due to the memory subsystem?
That is, infinite speed is very fast. But yeah, I mean, if we can actually keep all of our work in the first level cache, you would have a significantly fast machine. We can't really realize that. I agree with you completely. We don't, in practice, it's always the latency that leaves the first level cache that's causing.
To tell a local story, it's like complaining about the speed limit when you're stuck on 520.
Yeah, exactly. The potential is huge, I think is exactly the point that you're pointing out.
Normalizing to 1 on the Clover here.
Right.
No,
So
what is the minimum?
Yeah, exactly. So basically, the minimum performing of the 3 architectures, we normalize the whole cluster to.
Okay.
Yeah. So yeah.
So are these are all multi-threaded benchmarks?
These are multi-threaded benchmarks. Yeah.
So when you run on a Xeon, which I guess the little squares are showing that it has 2 CPUs,
Yeah.
and this stand has 4 and the West has 4?
Yeah.
So do you fork a different number of threads?
So in this experiment, I bin the work to 1 core, right? So these workloads are essentially a part of a suite of pre-made benchmarks inside of Google, which are composed of the commercial binary coupled with a giant log of hundreds of thousands of queries, right? That it just churns on a pre-made packaged log of queries. So it's called perflab.
Okay, so these
And you
are
can-
all running in 1 thread.
Right, in 1 thread in this particular
All right, so they get the
experiment.
whole memory system to
themselves. Yeah,
Okay.
yeah, exactly. They don't. So we don't see.
Each thread gets the whole memory system to themselves.
Yeah, exactly. So when we look at, so that's machine configuration. We observe a lot of variation in performance. Well, what about co-runners? So we also observe that when we take the same type of experiment, but only look at the degradations due to a co-runner running alongside this machine, we have a significant degradation in performance. In some cases, and not so much in other cases. So across the various clusters, we can see that, and the key thing to take out of this graph is as you change the co-runner, you can have a different amount of degradation. So we observe that the task performance is highly impacted by the co-runners on that machine as well, right? So
is the co-runner, you have 3 co-runners there?
yeah. So here we fill up the whole, because we're studying contention here, so we just fill up the whole chip with threads. So it's binned based on half the policy is half the cores are one application, the other half of the cores are the other application. Because we wanted to kind of, if we ran the experiment where we only limited it to 2 threads, we won't really see the true pressure of contention, given the memory system, right? Because you won't have as many accesses, memory accesses coming from the processor, from the various applications if they're limited to one thread. It'd be a slower rate. So that was the rationale to fill up the whole chip.
Okay, so again, each of these apps that you have on the x-axis, they get one core?
So in this experiment, they get half the cores on the machine.
They get half the
Yeah.
cores. Okay.
Yeah, so it's a half policy.
I imagine there's a lot going on these systems at any point in time, even in a performance lab. And I imagine that there's a lot of variability that you get just from running these things multiple times, right?
Yeah.
So are these means over multiple runs?
Right. So these are means over 3 runs. However, this PerfLab, it's called PerfLab, this benchmark suite that Google's developed internally, they've worked really hard to get the performance variation across runs down within the 1% range. So that's really what's used here.
But when you start adding interference, then you have timing issues of when you actually start the applications, right?
Yeah.
Is their harness handling that?
Yeah. So the harness here is handling it spawns both applications at the same time. The applications run for a while, so they run for 20 minutes.
Okay.
So we
minimize that.
Yeah, so we minimized it, but there might be a little, yeah. So the observation is that the execution environment has a significant impact on performance. And for this, I claim that exploiting, and not just exploiting, but adapting to diversity in execution environments is critical for improving performance and utilization in warehouse scale computers. So I've done a number of work dealing with these types of issues of optimization and the interaction between workloads and the underlying system across disciplines in computer science such as characterization, workload studies, compilers, static and dynamic analyses, runtime systems and software systems, and computer architecture. But today I'll be talking about a number of these works that deal with this issue of diversity in execution environments and how we can exploit that. So there's 3 aspects to the work. There's 3 design points that we need to acknowledge the diversity in execution environments. At the cluster level, we want to map jobs in execution environments they prefer. At the machine level, we want to enable jobs to adapt to the execution environment on the machine and changes in that execution environment. And then there's a very important event that happens within execution environment, important for utilization, the interference between tasks. And we want to be able to acknowledge and explicitly manage this interference to improve utilization. And that'll be clear in just later in the talk. So to summarize the contributions, I've developed an intelligent mapping approach that will dynamically learn how jobs perform in various execution environments using continuous profiling, and then exploit that knowledge to do this mapping. And that results in a 15% performance overall across a cluster. And this has been validated using the same kind of application I've shown, real production machines and real production workloads. At the machine level, I've developed a new mechanism that allows for applications to adapt and respond to events in the execution environment and solve 2 pressing problems in warehouse scale computers. The first is selecting your aggressive optimizations based on if they're effective or not dynamically. So you can dynamically detect if your aggressive optimizations are giving you a benefit, and then apply them only when they're giving you a benefit. And then also, we really need a mechanism in software, and this is actually, at the time was a challenging problem, is to think of a mechanism in software to detect that contention is occurring, right? To be able to positively say that we observe contention. And so I've used this runtime system to detect and respond to contention dynamically, which is important for utilization. And then finally, when dealing with the interference within an execution environment, when certain applications have a precise amount of performance they must guarantee. And certain co-locations between applications can violate or not violate that performance requirement. And I've developed a technique that can precisely predict which applications are OK to co-locate on a given machine to allow more co-locations to occur over a policy of just disallowing co-locations. It'll be clear when I get into it. And that produces a 50% improvement in utilizations of a 500 machine cluster in the scenario that I will present.
So in each of the scenarios, it's a 5 machine cluster?
Oh, no. So it differs from experiment to experiment. So at the cluster level, and these two works, the cluster level and the interference in the EE, it's 500 machines. Yeah. And we run an experimental scenario on those 500 machines using, canned executions, right? It'll be clear in just a few. So let's look at the cluster level. I'll be going through each of these cluster level, machine level, and interference. I'll be dealing with each of these in the talk. So we start with cluster level. So at the cluster level, really what we're trying to attack is the assumption of homogeneity in the way systems are designed currently. So many systems, like systems used at Google, they view the entire warehouse scale computer as a collection of thousands of cores and petabytes of memory. And basically, when a job comes in to be scheduled on this giant computer, it finds the first available machine with the prescribed number of cores and amount of memory needed by that job. Each job has a configuration file with a number of cores and memory needed. However, what actually happens is we do have this machine heterogeneity. And as I've shown you before, it matters a lot in the graphs I've shown where the jobs end up landing. So how do we exploit this? How do we take advantage of this just off the cuff? The first thing to do when taking advantage of this diversity. So we want to be able to map jobs where they run best, and we want to take advantage of the unique properties of warehouse scale computers to do so. So we know the application services that we're going to be running continuously on these machines, and we also know that we have continuous profiling as a service that lives in production, where we continuously can profile all of the jobs and to get performance information using hardware performance counters. In the case here, I use GWP. In this work, I use GWP, which is the Google-wide profiler. And there's a paper in IEEE Micro from 2010 that discusses that in more detail. So what I did here was develop this approach I call SmartyMap. And what SmartyMap does is it exploits this continuous profiling to build a knowledge bank of how jobs perform, scores of how jobs perform in different execution environments, defined by both the underlying machine configuration and the co-running jobs. And based on this knowledge bank, SmartyMap will train the knowledge bank and use it to map jobs in places where it predicts it will have the highest score using a Google-wide profiling. Question?
Is this based on production profiling or on the test cluster where you run these benchmarks?
The evaluation will show test cluster, but
the maps and the models.
Oh, this is live. This SmartyMap runs live and is with the continuous profiling information. It refines its knowledge of the different types of jobs running and the kinds of environments that it likes to run in.
So how do you incorporate sort of the variance in workload coming in and other noise that you see in production?
Yeah. So statistical methods is what we use. We would use the average basically that we observe across different execution environments to score.
And one more question: is the application sort of instrumented to tell you this is the start of a request, this is when it's done, so that you know how long it's taking? Because if you just see arbitrary, binary running, you don't know the latencies, right? The user would.
Right. So that's not factored in. So what happens is it uses hardware performance counters. So the profiling service continuously samples all day long, all night long, hardware performance counters across all machines, and then it also collects what was running on that machine. And then so we have all of these logs of just hardware performance counter information for all the jobs running as a service. So it does it at the hardware performance counter level, and it doesn't give you higher level information such as quality of service information.
So how do you know from the counters if this is slow or this is fast?
Right. So here in this experiment, I use a metric I call instructions per second. So I'll talk about it in terms of improving the performance we're getting from the whole cluster in terms of how many instructions per second am I getting from the cluster. Kind of thinking of the whole cluster as a chip, kind of. But it's kind of, I like it. Okay. So, go ahead, Kasha.
So why is IPC the right metric?
Right. So IPC particularly wouldn't be the right metric because we have different types of architectures. But IPS, which is kind of it's essentially IPC, but generalized to seconds because seconds is generalizable across
different
architectures.
clocks.
Right, right. But I think you're hinting toward a really good point, which is you may not be optimizing. You may not want to optimize strictly for how fast something is running. There might be other things you have to optimize for, and for that, you can use a similar methodology. You would just change the feature you're optimizing for, right? So if you could collect from GWP, if you could get a notion of, let's even make it as high level of how satisfied a user is. If you can use a continuous profiling service to see how satisfied a user is in from these types of services in different execution environments, you could apply the same methodology that I'll show, or the same approach that I'll show in the next couple slides.
So even though you're using instructions per second, your approach is general enough to handle other
right, and you'll see
okay.
Right, precisely, and you'll see on the next slide. And it's because we formulate, no, it's a great question. It's because we formulate the mapping problem as an optimization problem. So we can leverage standard numerical optimization techniques to arrive at a good solution. So we have an objective function, and we're just trying to optimize to that objective function. So that's how we formulate a problem. Given that we have this knowledge bank that we can refine these scores using the statistics I just mentioned, given this knowledge bank, what SmartyMap does is, whenever it has a set of jobs it needs to map into a cluster, it will internally
SmartyMap will simulate the different mappings using the information it has from the knowledge bank, and use a numerical optimization to optimize toward the highest performance it predicts that you can get from the cluster. So we use a simple stochastic hill climbing approach to perform this optimization. It works well for this kind of optimization.
Is this sort of a one-shot optimization that, when I have a bunch of jobs to place, I just optimize for those, ignoring everybody else and keeping everybody else fixed? Or, would you get additional benefit by sort of globally optimizing the whole thing?
Right. So how this works is, so imagine you want to turn a couple services on inside of a cluster. When you turn those services on, there's a set of many types of jobs that need to run. So when you have the set of jobs you need to run, you run it through an optimizer that will simulate use the knowledge bank to optimize to get the best aggregate performance it predicts. So it kind of works like that. I think you're hinting towards two issues, which is, what if there are things already running? And that would be where you start your optimization. You'd have things running, and then you would be simulating things being added onto those machines, and you optimize accordingly. And another thing I think you're hinting to, which is a great point, is what about changing the optimization dynamically? Can you move things around?
Or could you turn off that service that's already running for a while and shift it somewhere else?
Yeah, I think that's an absolutely fine idea, and probably would produce good results. But I didn't do that specifically. So I'm not going to talk too much about. Oh, go ahead.
How long does so it could take a long time to compute that, and you have some requirements on getting these jobs scheduled quickly. So what kind of deadline did you give yourself for the scheduling algorithm?
Yeah, so the scheduling algorithm we have here, and with the size of problems that, in the thousands of machines in a particular mapping scenario. So it takes, in a matter of seconds, you'll have a map that is predicted to be good by SmartyMap. And in this situation, we're not doing, so these mappings won't be done often, because it happens when you turn on the services in the warehouse scale computer. So you can kind of do that once. Let's assume you just want to have search and maps and mail running on cluster 5. You can do that once, and then let that run until you make a different decision. Like, all right, I don't want to run maps in that cluster. I want to move it to this other cluster. And then you can do another remapping. So it doesn't really happen
so it's not
at the query level.
As jobs arrive, it's just when the service gets turned on.
Right,
okay.
Right, exactly right. So as time passes, the quality of the knowledge bank improves because we keep refining it with new updated information. And I'm not going to get into too much detail about the specific classes of information you can use for mapping. Just leave it to say Smarty M, which is just if you were to only take information at the machine level, like jobs, if you were to only consider machines in the heterogeneous environment, what is the complexity of the amount of information you would need to collect? And then what if you were to take machine level plus all the permutations of possible co-runners, which the complexity gets much higher. And so I would just point to this because there's an interesting observation as to how Smarty map across these two things work. And I think I present that in the slide after this. So just to describe the experimental setup, just to see, well, how well does this Smarty map work? So we have 500 machines, 3 production types of machines. These are actually real machine types configurations used at Google, which might be interesting for you guys to see. I got approved to have that. I think it slipped past the approval, but because normally they wouldn't approve that. Anyway, and we have 1,000 jobs that we'd like to map. And I've used the 9 Google application presented earlier. There's 2 sets of experimental test beds. There's the Google one that I did at Google, and then there's an experimental test bed I used spec and off-the-shelf machines when I was not at Google to do the same experimentation. So what we observed, so I normalized, so this is normalized IPS, and it's normalized as if all jobs had the best machine it could run on, and it was running alone. So that's the normal, that's 1. And as you observe across the different metrics, the light blue bar shows what we'd expect currently, right? Where it doesn't take into account any of the heterogeneity across machines or co-runners. And then we show different classes of information that we would collect, but observe that so only these two, only the blue and the red show where we consider machines and not just co-runners. And notice that when you consider machines, you get most of the benefit, right? So the diversity across co-runners in the execution environment matters a lot less than the diversity across machines, which is a nice, interesting observation. But the interesting thing, and the paper that this is attached to that you guys haven't seen yet, the interesting thing is, right, it depends on how diverse your machines are, right? So across these 3 machines that actually exist in a real cluster, the diversity is relatively high, but it's kind of surprising because we're just talking about going from Core 2 to Core i7, basically, and having the Opteron competitor to the Core i7 in there. So the generations aren't that huge, and there's huge opportunity.
Doubling the size of the memory system.
Exactly.
From the previous slide.
Precisely. And the prefetchers got so much better, right? Especially from Core 2 to i7, they fixed a lot of things in the prefetcher. So you're absolutely right. Good point. So that's the result. But there's one more interesting observation. So we have a 15% improvement overall across those 2 examples. Now, one interesting observation in this, and this might be really useful to some of the data center people here, is that it tells you something about how do we build our clusters. If you were to acknowledge this diversity, does it change the way we would want to go buy machines to fill a cluster? And it does, right? So here we show applying the Smarty map to clusters that are fully composed of one of the 3 types of machines. And then we show clusters that are half filled with Clovertown and Istanbul and Westmere and Clovertown, the 3 different types of machines. And what we can observe is, oh crap. So what we can observe, oh no, all right, maybe, oh, I see, I was clicking. So what we observe is if you have all Istanbul versus having half Istanbul and an older architecture to Clovertown, when you're doing the optimization of mapping jobs where they like to run, you can match the performance of the newer machine cluster, which this one would be a cheaper cluster to build, and you actually beat the performance. Why? It's because some of those workloads prefer the Clovertown over the Istanbul. So if you can do the mapping right, you can actually have a cheaper mixed cluster and get matching or better performance, which we see in this case, which I think is really interesting and might tell us that we shouldn't just buy all one machine
Although your West number says we should just buy big
Yeah.
memory machines,
Yeah,
right?
Yeah, and that's because Wes is just such a strong processor. But if you look at at least if you look at the difference between the expected performance and the difference between when optimizing performance, you do a little better. You do a little better than if you were to randomly map. So that's why I don't want to, because this one is a little bit more subtle, but you have to look at, maybe there's another graph I would need to build to really show this point, but you get better efficiency. You can get better efficiency than the random when you're doing the mapping, is what I mean, going across the two. But you're right. In this case, you would just, for best performance, you just buy all Westmere.
Well,
Done.
but if you looked at performance per energy, the powering up that memory system is efficient. So you might actually be at a better energy efficiency point on one of those other two graphs.
Yeah, I mean that's
depending on how much it costs to run it.
That would be a very interesting data point to show, and I kind of wish we did that now. Because if I can tell you the energy benefit, that would be actually interesting. But yeah, so that's that result. So let's move to the machine level.
Ben had a question.
Yeah.
Oh, go ahead.
I'll start from my point.
Yeah, cool. All right. So at the machine level, we want to be able to allow jobs to adapt to their execution environment because there's a number of problems that require this, and I'll show why. So what we're dealing with here is the rigidness at the application level. So traditionally, when a compiler generates your binary is fixed regardless of where it runs in the execution environment. Now, there's a class of problems that would require this application to adapt to its execution environment. Two I'll highlight and address in this work. The first problem is the problem of aggressive compiler optimizations. These are optimizations that are known to either improve or degrade performance based on certain dynamic effects, right, or certain situations across different applications. So we would want an ability. In one execution environment, you may see a performance improvement, while in the other, you might experience a slowdown, right? So that's the first problem, that we need this kind of flexibility. The second problem is this issue of detecting and responding to interference online. So your web search job may be co-located, will have performance requirements, and may be co-located to some low priority batch applications. And currently, there's no way for us to know programmatically or to ask, well, are these jobs contending? And so, because if we could ask this question, and if we could get a response from the software system, we might be able to do something to reduce the interference that is generated. So the ability to detect and respond requires a runtime system to be there to ask that question to. But before we can address these two problems, we need a mechanism for cracking this rigidness, for allowing this online adaptation. And so when realizing this kind of mechanism, we have binary translators. This is for arbitrary native applications. So for arbitrary binary applications, we have dynamic binary translators. However, it hasn't been adopted in many production environments, including warehouse-scale computers, because they're huge in complexity and sacrifice a significant performance. And the argument of using these binary translators for optimization hasn't really been realized by our community in a convincing way for production. So to achieve deployability in warehouse-scale computers, we need an approach that is lightweight and low in complexity. So we need a new technology for online adaptation. And this new technology is one of the major challenges and contributions of this work, right? So let's take a quick look at conventional approaches to binary adaptation. So your application runs on top of a runtime, and this runtime is responsible for keeping fine-grained control at the instruction and basic block levels. So it uses something we call a code cache, and the runtime will dynamically translate the application at the instruction basic block level into this code cache, and then execution is only allowed to occur out of this code cache. If this code cache was to transition back to the original binary, things will break. So that's a big no-no. However, there's expensive transitions between the code cache and the runtime that occurs. So when we have indirect branches that are not easy to predict and on the critical path of your application. You may take many expensive transitions between the code cache and the runtime, and that's very expensive. And then to monitor the execution environment, you may need to add instrumentation. And then this instrumentation, to employ some kind of adaptation, might need to also make transitions to the runtime and back. So we have a lot of complexity, a lot of overhead, right? So we need a new approach for binary adaptation. So I asked the question, why not let the application run directly on the processor, right? And we can use a very tiny runtime that uses hardware performance counters to keep us informed about what's going on dynamically, right? So we have no fine-grained control and we execute directly. But you may ask, well, how do you adapt the application code then? So I advocate and propose that we use software, what I call scenario-based multi-versioning, where we can specialize instances and regions of code for dynamic situations we anticipate. And then we can just select which regions in code to execute when we experience that dynamic situation, right? So this is very lightweight, very, very low overhead to actually employ when you want to change your code dynamically. And then you get the compiler, so there's some added benefit over something that only uses binaries. So it's an interesting argument because there are things that you might not be able to do since you're not compiling dynamically, but then there's things you can do because you have compiler, but you have to statically, the caveat is you have to statically acknowledge what you want to specialize for dynamically. That's the caveat of this approach. And we also need, especially for when we want to coordinate multiple co-running applications, we need to enable coordination between runtimes. So we let this runtime system talk to each other so that we can have coordinated adaptation policies across applications. So this is the mechanism. So this is low in complexity and low overhead. So I'm not going to talk in too much detail about the runtime system, but I'll show, I call it Loaf, the lightweight online adaptation framework. But I'll show how this diagram can kind of summarize technically what's really going on, right? So for scenario-based multi-versioning. So basically, we have an application that each call to the region of code that you specialize statically for dynamic situations are indirect branches that use a table, a global dispatch table, to know which one is active, which version is active, and you can reroute execution dynamically using this dynamic introspection engine. So the beautiful thing about this approach is, as your program is running along as fast as it can, doing its thing with one particular routing, your dynamic engine can simply write new values into this table and then restructure, reconfigure how your binary is running. So you could think of it as a reconfigurable binary. And this is nice because as opposed to traditional multi-versioning where you have some kind of conditional that's on your critical path, if that conditional had to look something up in your environment, you'd have to execute it every time. But here, the program never has to itself, conceptually itself, pick what version to use.
But you're trading an indirect branch for a
direct branch.
Yeah, well, exactly. For a test that is going to, a branch predictor would probably get right most of the time. So isn't this actually more overhead than what you just said?
Oh, so there's a tiny bit of overhead. I've actually run the experiments. The overhead is less than 1%. Just if you were to, so the experiment to test that overhead was just keep these values the same and just let the application run, right? And that overhead is less than 1%.
The branch predictor works.
Yeah, and you're not changing.
It's a direct branch or an indirect branch.
Yeah, and when you're rerouting, you know, a lot of it depends on the granularity at which you're chaining this table. If you're chaining this table at milliseconds and tens or hundreds of milliseconds is when the next change comes, then you don't suffer a major penalty from switching the table too much. It's much lower than traditional approaches.
So this is the 1% was for redirecting every call through this table?
Right. Every call of it's not all the functions. It's the hottest functions. Every call to the hottest function. So kind of like every call, since they're the hottest functions. But
it's like Arnold Ryder.
Oh, sorry. Go. Yeah.
Arnold Ryder did an instrumentation framework like this for for Matt's PhD thesis. It's very similar, and they had the same kind of results even when the branch predictors weren't that good.
Yeah.
Weren't as good as they are now.
Yeah. Question?
There seems to be a testing problem. If you have 20 such options, you have over 1 million versions of the program at any one time, and of course an even bigger infinity if it's a long-acting bug.
Yeah.
What do the testing people say about that?
I haven't heard that comment before. That's an interesting point.
Your compiler correct.
But you're right. And you allude to a really good point. I mean, statically, if you want to do too much online, there's a state explosion, right? You can have all kinds of permutations of versions for different dynamic scenarios. So it's up to the optimization designer to design to not go too crazy with it, or it'll start to not be as performant. So yeah, that's an interesting point. So
Do you do anything, because now you have built-in versions, so you have code explosion. So do you do anything to control that so your iCache doesn't blow up in general?
Yeah, so I don't do anything explicitly. It's really everything I do is in the designing so you identify your dynamic scenarios and you specialize accordingly, and it's in controlling the number of specializations you want to do statically. But I don't do anything clever dynamically. But it's not hard to imagine coming up with some ideas to keep that state explosion. Actually, that's a very, very interesting point. Yeah, we should chat more about that. Yeah. So time to address those problems now that we have this runtime system. So I mentioned the two problems, SBO and CAER, aggressive optimizations, and detecting contention. So I'm going to talk about SBO first, and then contention-aware execution. So how do we use this kind of approach to detect when our aggressive optimizations are effective, and then use them only when they're effective? So I use an approach I call a competition heuristic, where initially throughout execution, you learn to identify whether or not aggressive, you try aggressive and compare that to the non-aggressive version, and identify which version produces the better performance using the dynamic engine that gives you performance information online. And once you make that decision, you let that run for a while before coming back around to do another test. And this functions continuously throughout execution. And so that's the competition heuristic. It's shown to work quite well. So on this graph, these are spec applications. I show the execution time normalized to O2, basically. It's just O2, no aggressive optimizations. And then each of the three bars, the blue, red, and the green, red, and light green bars, show the performance when statically applying these different permutations. And then the third bar is us. It shows the performance when you dynamically select the optimizations. And we consistently do better than our baseline, which is O2, the conservative approach, which is to not use aggressive optimization. So we get a clear win over the conservative approach, and by and large, we even beat statically applying any one dynamically. So it's pretty effective, and overall it's about a 4 to 10% performance gain across the applications over the baseline.
Which one is doing it dynamically versus the fixed?
So just this one.
The blue.
And all of the others are some fixed aggressive optimizations. No aggressive optimizations, cache prefetching, loop unrolling, and both cache prefetching and loop unrolling using the GCC 4.3. So we get about a 4 to 10% performance improvement there. And ask for my dissertation if you find any of this interesting. All of this stuff is in detail in my dissertation, and there's papers too. So now let's look at contention-aware execution, where we need to detect and respond to contention. So let's make it clear, what is this contention problem? So if we have multiple applications,
Before you get into this,
Yeah.
Can you give me a better sense when you're compiling sort of different versions of these hot code blocks? What's the difference between them? Are they like double levels of unrolling in them, or different?
Right. So
what
this.
different choices do you compile them?
Right. So the choices I made in this work were to use so GCC is configured for some canned heuristic knobs settings, right? So I used the canned MARC, the microarchitecture, maybe I'm getting too technical, but I use so the designers of GCC have selected values for loop unrolling, which is aggressive. And then they've selected values for how to do the heuristics for how to do the cache prefetching. So I've just used those. I didn't have versions for each knob setting, and this gets into the state explosion, right? Because if you have different versions, if you want each knob setting, you can start to really blow up stuff.
Like the unroll is unroll by 4.
Yeah, exactly.
I happen to have beat in my head.
Yeah, no, actually, that's precisely right. The unroll is unroll by 4.
That's the magic number. It works in all compilations.
4, just go 4. 4 and you can't go wrong. But that's a great point. You have to really think carefully about how you specialize.
So one of the issues in doing trials is that when you measure something at a fine grain, you could measure one instance of the loop that only has 10 iterations, and you could measure one that has 1 million. And so, of course, the one that takes 1 million takes longer, even though it is the faster version, because it's optimized more correctly for the 1 million version, right?
Yeah.
So how do you take in that account, or are your workloads so homogeneous that you didn't see that very much?
Yeah. So I use that's a good point. I use a kind of a coarse granularity. I use in the milliseconds, so it's 10 milliseconds for comparing the different versioning schemes, so the space of versioning schemes. And I refresh the information continuously, right, after some fixed amount of time. I think it was a couple seconds. So these are spec applications, right? So after a couple seconds, it would just do the evaluation again, aggressive, non-aggressive, and update. So it's really dynamic, truly dynamic in that sense. Does that answer?
So you just are making local choices based on the current averages?
Precisely. Absolutely correct, yeah.
And how do you alternate between the versions? Are you running 2 separate versions and measuring both of them, or are you switching between them?
Switching between them using that rerouting capability that I. Okay. So just updating that table.
You could get unlucky because you
switch at the wrong time and you get the wrong, you make the wrong decision.
But you're not seeing that in your results.
Yeah, not across these applications. So that's good. All right, so what's contention? So when you have multiple applications, if the working set of the application fits neatly into the early levels of cache, we don't have interference. We get to scale with the number of cores. However, as soon as we use shared resources, like the shared cache or the bandwidth to memory, then these applications can slow each other down by contending for these shared resources. So that's that's how we get interference. Now, in warehouse scale computers, this is particularly problematic. If we have application A and B run on its own machines, they'll run full speed. However, as soon as we collocate them on the same machine, we can have a performance degradation. And a high priority application may have a quality of service requirement that it must meet. And so for this reason, in warehouse scale computers, the collocation between high priority applications and other applications are simply disallowed. It gives the whole machine to the high priority application. So that actually wastes potential utilization. And this is because not all potential co-runners will degrade the performance of our high priority application. So if we can do a check dynamically to see, are these programs contending, we can identify those that don't have any contention at all, right? So what we need to do is have a runtime approach that can detect contention. So at the time I did this, a lot of folks told me, from software, there's no counter for contention. Like, if you have a dip in performance, how do you know that it's actually contention? So is detection possible? Well, I came up with this approach. I call it the shutter approach. So on your runtime, you have this is the high priority latency sensitive, and we have a batch application. The runtime can shutter the execution of the low priority application. And if it observes a corresponding spike in last level cache misses corresponding with the shutter of the low priority application, then we can assert they're contending, because we see it with the little test. It's a little online test, and we can see that they're actually contending. And so we do this little test, and then we can know their contention. And there's a whole number of ways you can respond. You can respond by killing it. You can respond by slowing it down, which is what's in the results I show. You can respond in a number of ways. But the cool thing is you can rule out those that don't contend at all. You can let those run with your little shutter approach. This also works quite well. Uses the same runtime infrastructure that I presented before. This also works quite well. So basically, what this graph shows is it'll show the degradation across these spec applications when co-located with LBM. And when we just allow co-location, the degradation can be quite high. But when we co-locate with CAER, then the degradation is significantly reduced. So this is across two different heuristics of applying CAER, significantly reduced. For brevity, I'll just tell you that we get an average of 60% utilization. And we reduce the interference from 17% to 4% on average, and get 60% of utilization from the neighboring core, right? So this experiment was done with two cores on the machine. And so with the 60% of the neighboring core, we get an overall improvement in utilization on that machine by 30%, right? Where we are allowing the co-location and getting the reduction here. The problem with this is that it's not precise, right? It doesn't deal with performance requirements. And the next part of my talk deals with just that. And that's the bubble up work, which I'm going to get to right after this question. Yeah, cool. And so, so there's some insights that comes from this that I really believe is how we should think about doing software runtimes as we move on. I think it's good to allow some vertical integration. So what I demonstrated was integration between the compiler, the runtime, and the architecture in developing dynamic solutions. One option is to involve the compiler to stitch in reconfigurability in our binaries. I think that's an opportunity. That's something we might want to think about doing. Performance monitors are the key to enabler of online techniques moving forward. And we really need to think about how to build monitors, not just for debugging, but also for online dynamic techniques. The approaches I presented are realizable today, and I believe will gain more traction as performance counters are built into the application binary interface, right? Where currently, there's a lot of systems where if VMware is using your counters, you can't use them. As soon as we have this built into the application binary interface, we'll solve that. And I believe ultimately the day will come when all code and systems will be continual restructuring, like the warming of a cache. Okay, so finally, I'd like to show how we can manage and measure this interaction, this interference, so we can allow for precise predictions and precise collocations. So what does that mean? So some applications have strict performance requirements, as I mentioned below. And some applications that interfere, we can allow if it doesn't hurt our performance too much to violate that requirement. So here's a simple example. If we take Search Renderer, now each one of these bars shows the performance of Search Renderer when co-located with each of these applications. Now we're back with Google large-scale, real, large applications. And what we observe is when we co-locate Search Renderer with each of these applications, Search Renderer's performance is impacted variably, right? If we have a 90% performance requirement, I'm going to call this the quality of service threshold, then some of our co-runners violate that performance requirement, while others do not violate that performance requirement. So what we want to do is be able to identify all of the collocations that don't violate that performance requirement for precision because of this over-provisioning of resources we have, where latency-sensitive applications get run alone and we waste those cores. So we want to eliminate the uncertainty of that interference penalty. And we want to precisely predict the impact of quality of service to allow safe collocations. So the goal is to have a general methodology that's platform agnostic. It can run on all those machines I presented before, and is deployable at the scale of warehouse-scale computers. Now, there's a lot of work that predict whether an application is contentious, but we don't have a way to predict how much it will hurt each other when running together. If you profile two arbitrary applications, we don't have a way to know how much they'll penalize each other from a performance standpoint when running together on the machine. And here we're trying to capture an interaction with resources that are not explicitly manageable or visible to software. A quadratic brute force profiling methodology is straightforward. You take all of your possible jobs and collocate it with all the other possible jobs, but that's not suitable at the scale of warehouse scale computers, as jobs are updated frequently, and there's a large number of different types of jobs, so it doesn't work at the scale. The question is a linear approach possible? Can you look at each type of job once and then tell arbitrarily how much they will interfere with each other from a performance standpoint? Especially considering that impact is based on the interaction with the co-runner. So the insight that led me to this approach is that given a white box approach where we try to analytically be able to analytically model all of the different aspects of the processor, the prefetchers, the caches, the interconnect, bandwidth, memory controller, replacement algos, queues, buffers, and even the secret sauce, which is private, like how the prefetchers on real architectures work. It may not be the right approach. It's high in complexity. It's not portable. You'll have to do this for every type of machine, do work for every type of machine. And it may not be feasible because of this secret sauce stuff, if this really matters a lot with the performance. So the question is a black box approach possible, where we can just treat the whole memory subsystem as a black box? So it's lower in complexity. It's portable. You can move it to any black box and run the same approach. And it's deployable on real systems with secret sauce stuff. So when thinking of this approach, I'm going to use an analogy I call the man or woman in a dark room, where you can think of the memory subsystem as a dark room where you try to feel. In a dark room, you could feel out the furniture. You can kind of get an idea of the layout of the room. Can we do that as a methodology? And that'll come in the slide after next. It'll be clear how that actually plays in. But first, let me tell you essentially how bubble up works. So we capture a representation of sensitivity and a representation of aggressiveness of each of the applications. And when deciding a co-location, we take that representation of sensitivity and the aggressiveness and combine them to produce the performance degradation. And it'll be clear from this animation. So we have a representation, from our profiling, we have a representation of sensitivity, which is a sensitivity curve, which you'll see. And then we have a representation of the co-runner's aggressiveness, which is the aggressiveness score. So when we want to predict how much they will hurt each other when running on this real system, we can take the sensitivity curve, and we can also take the aggressiveness score, and the sensitivity curve shows on the y-axis, it shows quality of service as you increase this notion of pressure in the memory subsystem, and you'll see how that works in the next slide. But you can take this aggressiveness score and use the sensitivity curve to predict an actual performance level when co-located. So then the question becomes, well, how do you get this magical, awesome sensitivity curve and these aggressiveness scores? Well, we use a bubble to produce the sensitivity curve and a reporter to produce the aggressiveness score. And this is where the analogy comes in. So the bubble is essentially a stress test that provides a performance dial where you can turn up the pressure on the memory subsystem holistically. Just using loads and stores from the application, you can turn up this pressure dial that holistically turns up pressure on the memory subsystem. And as you turn up this pressure dial, as shown in this animation, you generate a curve as to how the performance degrades as you increase the pressure on the memory subsystem. And that's how you get the sensitivity curve. Now, to get a score, use a similar kind of intuition. You have a reporter that sits on the memory subsystem, that has a presence on the memory subsystem, and you let your application run alongside that reporter, right? And what the reporter, it's trained to know, it's complicated how it's trained. It actually has trained a sensitivity curve in itself that's used in reverse, but I'm not going to get into too much detail. But it's trained, and it basically reports how much it thinks you're hurting it. It basically reports how much it thinks the application, what its aggressiveness score is, based on how its own performance is being affected. So that's how the reporter works. So these are the two steps of the profiling approach. You take each application and you run it through this profiling approach. So what is this bubble? Well, how can we conceptualize the bubble? Well, if you take the degradation on some application by a co-runner, A and C, you can conceptualize the degradation as the summation of all the sensitivities and pressures of sensitivity of application A and the pressure on some resource I, R sub I, and the pressure of the co-runner on that resource R sub I. And essentially the bubble is this approximation of this actual degradation by replacing the co-runner with a bubble of some k, where k is closest to the co-runner. If this isn't landing, it's all in the paper and the dissertation. So, and so when you have this approximation, we do have a source of error. And that source of error comes from the difference when you replace that C in the actual degradation from the bubble K. So there's a hypothesis. The hypothesis is if you design the right kind of bubble, you can minimize this potential for error, right? And so good bubble design is key. And in the paper, I actually outline the systematic principles for designing a bubble. If your bubble stress test software application has all of these properties, it should be a very good bubble, very small error. And so it's monitoring curves. The details of this is in the paper, and I show how I achieve each of these three things in the paper. But let's look at how well Bubble Up works. And I have some backup slides that even show even more how well it works. But so let's take this is actually very important to understand the next graphs coming. The experimental scenario, we have 500 machines, and each machine has 6 cores, right? Search Renderer is configured to use 3 cores. And each machine is running Search Renderer. So we have 500 machines half loaded with Search Renderer, right? And we have 3 cores available for the core runner. So we have 500 jobs that are ready to run. And it's an even mixture of the 17 Google workloads, right? Randomly selected mixture of the 17 Google runners. And basically, we allow colocation that is steered by Bubble Up, right? So as opposed to having each machine only run Search Renderer, which is kind of the current approach, we'll allow colocation, but only the colocations that Bubble Up says are OK, right? So our baseline is basically those 500 machines half loaded. So we're at 50% utilization, right? Now, if we say, OK, Bubble Up, please allow all of the colocations that don't violate our program, that doesn't degrade our program by more than 1%. Allow the ones that essentially don't cause contention. I'll allow a 1% leeway. Then this is how much utilization improves as you change the QoS policy, that line that tells you what you have to guarantee. So at 99%, we're already experiencing significant gains. And at 90%, we're beyond 80% utilization. So we have a significant improvement in utilization. So overall, at the 98%, we have about a 50% improvement in utilization by letting Bubble Up steer 98% of the quality of service. But I mentioned that there was a potential for error. And so Bubble Up can potentially make mistakes. It can predict that a colocation is safe, but then it does violate the quality of service. That could happen in some degree. But we observe that when that does happen, it's severely small violation, right? So in the worst case, we have a violation of 3%. So all of this blue are correct decisions made by Bubble Up, right? And then the other colors show slight violation. So a 1% violation, the worst we get is a 3% violation. It's actually a 2.2% violation, but it's between 2 and 3%. And this is across these 17 large real-world applications. And actually, in the paper, I show how if you change how you define your QoS policies, you can bring this down you can significantly reduce violations and bring it down to 0 if you change how you define your QoS policies. So this is a huge step forward. Go ahead.
What if I were to just have a policy of just adding in maybe a tenth of the co-runners or a third, or randomly allocating them, right? So do you have anything that you compared against? Right, so you've provided a policy to describe when and where things should go. Yeah. But I could imagine just a random one, right?
Right. Just randomly collocate anything. Well, this top graph, that's an interesting point. This top graph might be helpful for that. It shows the number of violations that you would have, the absolute number of violations you would have if you allowed all collocations, right? So if you just allowed everything to co-run, this is how much violations. If you let Bubble Up co-run, that's how many violations you have. And on top of that, the violations are very, very small. So in the worst case, if you say I want 95%, in the worst case, which is very small, you get 92%. across these workloads. And you can change the way, you can incorporate a tolerance in your QoS policy to reduce the number of violations if you're contract confined. In fact, companies like Google and web service companies aren't contract-like. It's not like they'll lose money. It's just their latency will be 3% more than they want. So this is actually a very big result for when you have web services that you're providing, software as a service. So that's pretty cool. And then it's general. It applies across architectures. Here are two totally different kinds of architectures, right? And we let Bubble Up allow the co-location across these two very different memory subsystems and hierarchies. The same bubble, the same reporter, the same designs, everything's the same. You just blindly move Bubble Up on a different architecture, and it works just as well. And to be clear, just as well doesn't mean it has as many co-locations. Just as well means it predicts the co-locations, because remember, these processors have smaller caches, smaller subsystems, so you won't be able to have as many co-locations at a given quality of service level. So Bubble Up works quite well here.
How many cores do those machines have?
Oh yeah, and it's the same half-loaded policy where we do half the cores and half the cores. And the K7, so the Core 2 has 4, and then the AMD one has 6, and the Westmere has 6. So it's 6, 6, and then 4 for the Core 2. But these only show the Core 2 and the AMD. The other results showed the Westmere on the Westmere architecture. So yeah, and basically it's all the machines are half-loaded or full-loaded policy.
Does your reporter function need to be tuned to the architecture of the specific machine?
No, that's the beautiful thing. It's the same reporter, the same bubble, right? And you just increase that pressure. And the reporter programmatically.
You have to measure it on the new machine?
Yeah. You have to run the profiling on the new machine. On every machine, you have to run the profiling. So you profile your applications on the given machine, and then you can predict arbitrary collocations. So that's yeah. But that might not be necessarily necessary. I mean, I don't know. It's tough. That's a good, interesting point. But I think there's a lot more interesting kind of cool things you can do with this kind of approach, and I'm really exploring future work. So I've presented how we integrate an awareness of execution environments at these 3 levels, and now I'll just talk about what's next. What are the kind of things? What are the areas of research that I'm planning to jump right into? So the first little vision that has many components associated to it is to have the warehouse scale computer be an autonomous sentient entity where it's continuously self-aware of all the execution environments within the warehouse scale computer and dynamically responding and optimizing. You can imagine having automated learning and reaction to historical data where you can derive policies from observing anomalies. So if you learn, for instance, when this job has to make an RPC this far away most of the time, that job over there is going to suffer something. So you can find these little patterns and then derive automatically policies from them. And you can imagine using machine learning to assist with that. So here you think of the data center as a robot that's continuously self-optimizing. And you can also think you might want to express to that robot policies, right? Like you might want to tell the robot how to deal with certain situations, and how do you program this robot? How do you design a language that you can express things like responses and sensing and execution environment? It's really a language for performance anomalies in warehouse scale computers. And so I wrote a grant on that, and it was funded by Google. There's a lot of excitement about this particular idea. Another idea I want to go into is the notion of accelerating warehouse scale computers, right? I mean, there's a lot of, in our phones, we have IP blocks, we have accelerators in our phones for different common workloads that we run all the time. At the scale of warehouse scale computers, we have the same environment. If Samsung can build an SoC, why shouldn't a Google or a Microsoft or any of these companies? So what you would have to do is find the common algorithms. What are the common things? There's a lot of machine learning that happens real time. right? That should be something that we can build an IP block for, we can accelerate. And we got to get a taxonomy of these different types of workloads that are amenable to acceleration. And then we can start designing custom hardware for these different approaches and continue to argue to Google or Microsoft or any of these companies that, that really this is the right way to go because you can save significantly. So just two more. I really think there's a lot of opportunity, and it's an emerging momentum in integrating software with architecture. Vertical integration and hoisting complexity, right? Where we let the architecture, let the microarchitecture expose things to the software platform, and then take advantage of that. I think one interesting philosophy of doing that is in the hybrid architecture design. It's transmetal-like designs, where you have a software component to the chip, and there's binary translation going on. It's actually really kind of, people are starting to look at that commercially, and I think that we don't really know what they can do yet. And I think they can do a lot. And I want to realize a lot of this potential and just demonstrate the greatness of it. Software, okay. So, and then finally, I think that we don't have enough research. We have a lot of research in the hardware community on accelerators and SoCs and so forth, but we don't have enough software systems. We have some, but we don't have enough attention being paid to how do you build the stack on top of, how do you abstract specialized types of specialized cores? How do you abstract it so you make them specialized, but then you generalize them as much as possible, right? What are the right kinds of systems that we need for that? So that's another promising area that piques my interest. And with that, I'll take questions.
Questions? Thank you.
Thanks.
So I'll just throw out something. So you're talking about sort of the kind of the commoditization of these data center components, and I guess the assumption there is that there's a market for such components. So the question is, if there's only 3 companies or whatever, 4 maybe in the world that build these data centers, how many are there really? Then who's gonna where's the market?
So that's a good point. So those few companies have scale, right? They have volume. So a lot of like chip architecture companies like Intel pay a lot of attention to them. However, I would look at the trend more broadly. I would look at the fact that the kind of applications that we're using computers for, a lot of that computation needs to live in that kind of environment. And we can imagine maybe we would have a lot of smaller companies that have their own little data centers, or we have a few big companies that have their infrastructures. I think regardless of how that looks, I think we'll still continue to have more and more of our workloads running in the cloud. But it's an interesting point. That's always a question with how much complexity and cost do you want to invest in something. You have to always think about, does it make sense economically, right? Like, what are the economics of what you're proposing? Is having an accelerator does that make sense if there's only like 3 of them that you'll need to? So it's a great point.
I'm a little curious, you really focused a lot on the CPU and its systems. What about other components? I mean, if you took the exact same system and I changed from standard spinning drives to SSDs, how much different dynamics does that cause these applications?
No, I mean, it's
utilization.
I mean, so the scope of this work really deals from memory up through the software, through the cores, through the software stack. That's really how I focus this. And there are a lot of applications that never really leave memory. Like, like web search is one where you shard the index over some number of machines, and then the query just gets sharded out, sent out, and then the search never leaves memory. It never goes to disk, and then it comes back up with a result. But there are applications that you do go to disk all the time, like mail, right? Like where you click on some random email, it can hit a disk, right, over there somewhere in the cluster. And it may not even be the same machine with the query. So then the bottlenecks change completely, right? The bottleneck becomes I/O, and it becomes network, how congested the network is. So my work doesn't go to that level, but I think a lot of the principles that I kind of expose here applies, right? Like you could imagine having techniques for sensing how contended the network is, right? They might be also, so I think in the network space, there might be more opportunities in hardware. Like you can have something that asks specifically questions, but yeah, you can have a lot of the same principle. You may be able to have something like bubble up for network I/O to disk. You can contend for the bandwidth to disk and so forth. You can imagine the same kind of techniques. Many might translate over, but it's very interesting.
I think that the other parts of the environment are a lot less predictable than your memory controller, because you're running, say, 2 applications on the same machine. That's different than running, there's 1,000 applications on the network, right? And you're getting random traffic, random bursts of traffic. The disk might be also, just because of how physically it behaves, is a lot less predictable, right? So building these kinds of models might not be as easy.
It's
But
definitely a different
really, I
problem
think the next step would be sort of to bring it up a level, and can we do it across the whole data center, not sort of per machine?
No, I think that's a great point. I know it's actually, there's a lot of researchers that are doing a lot of interesting in the network right now for this exact same space. So yeah, I hope to collaborate with a few. Yeah.
Right.
Thank you.